Hello everyone and welcome to this webinar. Thank you very much for your interest in our products. My name is Andréane. I'm the product manager for PEC at Eddyfi.
And I'm Vincent Carpentier. I'm an R&D engineer. I work on the sizing algorithms for the Lyft.
This webinar presents our new dedicated solution for the inspection of insulated structures that are protected with galvanized steel GS weather jackets. If you have any questions during the presentation or you want to interact with us, you can use the menu at the bottom left of your screen and send us any question that we will answer at the end of the session. During the presentation, we will go over the basics of the technology. What are the impacts of galvanized steel weather jacket for PEC inspection, the benefits of using our new patent pending probe that was developed for this application. We'll also perform a live demonstration with our standard probe and our specialized probe. We'll do some data analysis and we'll go over other software development that we introduce in the latest software release 1.3. Why use pulse eddy current? It's a screening tool, an electromagnetic inspection technology that is used to detect defect and corrosion in ferromagnetic materials. So it can be used over various types of lift-off that are sometimes coating, concrete, composite wraps. It can be used for the detection of corrosion under insulation, protected or not with weather jacket, over marine growth, over also external corrosion products such as scab and blistering. It's a very versatile solution. This video explains what happens during the acquisition. The PEC probe will pulse a magnetic field that will penetrate the thickness of the material. The abrupt cutoff will induce strong eddy current in the part, and we measure the decay time of those eddy current to measure the thickness of the remaining material. If there is some corrosion in the line, this will reduce in a steeper decay. So that's how we will measure the remaining wall thickness. For this webinar, we will focus on a very specific application, which is the detection of corrosion under insulation. Usually, we use a weather jacket to protect the insulation. The common types are aluminum, stainless steel, and galvanized steel. Being ferromagnetic, galvanized steel weather jackets induce some problems during PEC inspection. We are very proud to launch a complete solution for this particular application, and we will first go over the adverse effect of this material to understand how we can better inspect it with our new patent pending probe. First of all, because the jacket is ferromagnetic, it screens a part of the magnetic pulse and the energy that is induced in the part. So you can see in the simulation here at the left, the signal is much more intense than the one that the probe can sense under number C when there is 1 millimeter of galvanized steel weather jacket. This is because the weather jacket will support some eddy current and also screen a part of the magnetic field. It also generates a parasite PEC signal at the beginning of the signal, masking a portion of the signal. So this can lead to hiding a defect that are smaller than the probe footprint. This graph shows the contribution of the GS weather jacket with the black dashed line. We see the signal when the blue signal is when there is no weather jacket, and the red signal represents the signal with the galvanized steel weather jacket. GS weather jacket also results in increasing the probe footprint, the magnetic footprint, so that will lead to more severe undersizing and a larger minimum detectable defect when we use our standard probe. And because the jacket interacts with the pulse of the probe, it induces some noise in the signals. So our new probe is designed to make sure that there is less noise in the signal as much as possible. Okay, let's start with a demonstration of an acquisition with our standard G2.
Yes, so for this demonstration, I'm going to be using this component. This is an 8-inch diameter pipe. It has 2 inches of insulation, and on top there's a weather jacket of 0.5 millimeter thick galvanized steel. So this, I want to stress the fact that it still works with galvanized steel, only it's suboptimal, and the new probe is going to make it much better. So yes, I already created the component. This way. All right, I already created the component. So if I go from the back stage to the front stage, and the first thing I will do is I will run a SmartPULSE on my component. In this case, I'm using only a G2 medium probe. And as you can see, the data is going to be quite noisy. This is because I'm not using the probe shoe. So what happens here is that much of the signal is attracted by the galvanized steel, doesn't reach my component. And also, I don't know if you can hear it, but you can actually hear the talk, talk, talk every time there's a pulse. That's because of magnetostriction occurring in my jacket, and it creates vibrations, and this is really bad for size and quality. So in this case, as you can see, without the shoe, I need an averaging of 16 to get 1% variability. So very bad signal shape. Even at 32 averaging, as you can see here, on the left-hand side, my A-scan is still pretty noisy. So what I will do is we'll put the probe shoe, which we sell separately, that really helps with this vibration problem. So if I put it on, just a second, then I'll run again the SmartPULSE, and I should get something much better. Yes, so if I relaunch the sequence, right away you don't hear quite as much the talk from the probe, so that's a good sign. Now it's calibrating. All right. Now, anytime now. All right, as you can see right now, if I use an averaging number of 2, which is suggested, I'm all the way down to 0.4 averaging. So I'm roughly 10 times better than I was. So it's pretty good. However, as Andrén was saying, some of the signal is actually absorbed by the jacket. So if I go into the advanced settings and I look at the gain used for this channel, 44 dBs of gain. This means that I need that much signal to boost it because the signal is a bit weaker than it should be. We have this rule of thumb that for every 0.5 millimeter of galvanized steel, it's roughly the equivalent of having 1 more inch of insulation. So I have less signal. If I was working in a noisy area with electromagnetic noise, like you would be on an oil refinery, the signal to noise ratio would be not quite as good. Now, if I start the acquisition, take a few data points, you can see the data quality is pretty good. This is where I calibrated, so I'm getting 100%. But if I go on top of a smaller defect, right here, what I read is 95%. This is a small patch of corrosion. It's smaller than the footprint. And as you will see very soon with the other probe, in this case, the footprint is enlarged by the effect of the galvanized steel. So it reduces, it basically causes more undersizing. So I'm only seeing 5.5% wall loss for this patch of corrosion. Now, this brings us to our patent pending GS probe.
You will have more accurate sizing when you inspect defects that are larger than a probe footprint. But you can still perform the inspection with the standard probe, but we recommend our new patent pending probe because there are still additional limitations to a PEC inspection with galvanized steel on a standard probe.
All right. All right, so there's a few things that you will notice with the GS probe. First one, it's magnetic. You'll see it right away when you put it on the galvanized steel. It actually sticks there. I don't have to hold it. It's pretty cool. What's going on here is that the magnets are going to saturate the galvanized steel, and basically it's as if the galvanized steel was not there anymore. We actually see through it. There's a few things that you need to consider, but first we'll run the SmartPULSE, see how that goes. So back to the front stage, SmartPULSE. All right. Now, you also can barely hear the magnetostriction, so that's a good sign. In this case, it's not only that we have a probe shoe, it's actually integrated, but also the magnet really holds in place the jacket so it doesn't really vibrate every time you pulse. So I should get pretty good variability. As you can see, with an averaging of 2, I get 0.5, which is roughly the same thing I was getting earlier. However, first big difference, if I go to advanced settings, and I look at the gain, now I'm only using 38 dBs of gain. This means that I need 6 less dBs to enhance the signal. It means that my signal is actually twice as strong. So if I was in a noisy area, I would get twice as good signal-to-noise ratio. So that's really good. Now, there's a few things to consider for every acquisition, but it's especially true in this case when you're working with magnets on galvanized steel. It's really important that the probe is stable. You don't want it to wobble like this. So we did a few things. First thing you'll notice, there's no longer any buttons on top of the probe, because we found that as you move your hand to go press the buttons, it was bad for the stability of the probe and bad for data quality. So we put the button right here, roughly 2 feet away from the probe, so that you can concentrate on keeping your hand steady and you can do the acquisition by pressing this button. Other thing we did is that we put on the probe some stabilizers that you can see on the sides. I think we'll have a picture on the website. But it really helps with a curved surface like this pipe is. Essentially, it prevents it from wobbling like this. So it's kind of holding it like this. So all these things really improve the stability and the quality of the data. What else? Yeah, since the probe is really sticking to the surface, there's a tail at the end to really help you lift it, to make it easier. However, we recommend that as you move around to take a grid on your sample, it's better to slide it than to raise it every time. As you can see, it goes fairly easily on top of obstacles like this strap right here. I don't know if you see it. All right, so if I take a few data points with the stabilizers on, close to my, this is where I calibrated, so I get 100. But now if I move to my defect, same as before, where I was seeing roughly 5% wall loss, now I'm seeing 10% wall loss. And the result is fairly good repeatability. So what happens here is that the footprint is smaller, so I have less undersizing of this small patch of corrosion. Yeah, I think that's the demo.
Can I have back the cable, please? Yeah, thank you. Finally, the new patent pending probe is designed to reduce the jacket permeability, improve signal penetration, reduce the probe footprint, leading to a better sizing and a better detection capabilities, and is also designed to effectively prevent mechanical vibration in the signal. When you have good signal quality, you can also use the CWT to perform a more accurate sizing of defects that are smaller than the probe footprint. Those are the thickness limitation on which you can use the probe. It cannot be used in contact. First, it can break scab material, by example, because of the magnet. We don't recommend it as well because it can leave residual magnetization in the part and affect further PEC inspections. So with this probe, you can cover up to 38 millimeter of the part thickness, insulation thickness up to 150 millimeter, and galvanized steel wire jacket up to 1 millimeter thick. Here we have an example of 2C scan. It's the same part. One data was acquired with our standard G2. The other one was acquired with the specialized probe. You can see there's a flange at the right, and this defect here is not detected by the G2. When we look at the results with the GS probe, because the footprint is smaller, the signal is less affected by the mass effect of the flange. So you can now detect that indication. the signal is also much less noisy, and you have a better sizing on small indications. For 1.3 now,
yeah, there were many smaller improvements that were made. First, we want to mention that the sizing algorithms are improved every iteration. We make them slightly better, more resilient to noise mostly. But there are a few quality of life changes that I think are worth mentioning here very quickly. So if I'm back, now you should be able to see my screen. I'm back in the same scan zone. There's a few things that we improved. The biggest one is the feedback we gave to the user as to data quality. So is the data point you took, is it good, and can you trust the sizing you get? So if I do something I shouldn't, so if I remove the stabilizers and I just wobble the probe around like this, and I take a few data points, as you can see, I get this signal distortion warning here in the top right corner. This is a yellow warning, and it tells you basically that the signal is distorted, and you should retake this data point. We have a color code now. If the warning is in yellow, it means that you should retake the data point, but if you keep taking it and you're getting the same result, or if you're back at the office and you see this, it means you should take this measurement with a grain of salt. If I go really crazy and I really move a lot, then I can get, yes, this, I get a bad fit. So in this case, the expected shape of the curve is so different from what it should be, because I was wobbling so much in this case, that the software is telling you, I cannot do anything with this, nothing that you could trust. So we give you a gray space and a bad fit message. The great thing that we try to improve is understanding of what's going on. So if you actually click on the error message, so I click on the warning, then you're prompted with this window that tells you exactly what happened. So in this case, I had a bad fit. You see the probable causes. You have 6 of them. Things that could have happened, but also on the right-hand side, you see suggested corrective actions. So it helps you on the spot understand what's going on and what you can do to fix it. So that's one big improvement. Second thing I wanted to mention, I'll need to leave the scan zone, is sometimes when you're scanning, there's not only a possibility for insulation and weather jacket. Sometimes in addition to this, let's say I'm working on corrosion under fireproofing, so CUF. In cases like this, you have insulation. It's going to be concrete, say, I don't know, 2 inches of liftoff, but you don't have jacket. However, inside you have wire mesh or you have reinforcement bars. And these can actually affect the sizing. So now you have an option that you can click when you're creating the component, where you're telling the algorithm, I have wire mesh, and the sizing algorithms are going to take that into consideration to give you more accurate measurements. You can actually see the picture on the right-hand side is updated with those dots to show that you have something inside the insulation. It's going to give you better sizing. All right.
Filter.
Oh yes, dynamic line filter. All right, one more thing, sorry. In some situations where you have lots of electromagnetic noise, one thing that can happen is that that noise is going to shift through time. So if it's not stable, maybe you're moving around closer and closer to a big motor that is emitting lots of noise. In some cases, what we found is that you can use a new type of filter that we implemented in this version that we call the dynamic line filter. So you go to Advanced Instrument Settings, right here, Advanced Settings, and you can click Dynamic Line Filter. It's on a case-to-case basis, so that's why it's not by default. But in some cases where you have strong electromagnetic noise that disrupts the quality of your measurement, you can try this, and it may help.
Great, thank you, Mason. That's it for the webinar. Thank you very much for your time. We will now go with the questions that came during the presentation. Let me just check. Okay, first question. What minimum liftoff can be inspected with the GS probe without impacts on the part under test?
Well, as we said during the webinar, you should not be using this probe in contact because of the magnet. You don't want to magnetize the component. So the minimum liftoff recommended is a half an inch of liftoff. So that's 12.7 millimeters.
Inspecting in contact can also leave residual magnetization in the part and break the scab material. So yes, it's a minimum of 0.5. Another question, are small and large GS probe available? We don't have, at the moment we have the one equivalent to the medium, which cover most of the application. If you need a larger probe, you can contact us and we can design one for you on request, no problem. We recommend, as mentioned, to use the small probe for contact inspection, but the standard G2. What's the maximum part temperature on which the GS probe can be in contact with during inspections? The maximum temperature is 80 degrees Celsius, about 175 Fahrenheit.
Yeah, that's the temperature for the outer part, for the jacket. Obviously, the pipe underneath can be much hotter.
Yeah. Can the GS probe be used on other type of weather jackets like aluminum, stainless steel, or other insulation? The answer is yes. The probe can be used over stainless steel and aluminum weather jacket, no problem. The only thing is that we don't recommend to do a dynamic scan with this probe because it will induce additional noise in the signal when you have the galvanized steel weather jacket. So there is no encoder option on the probe. So the productivity will be limited to the grid mode for that. Even on other type of jacket, you will have, it's comparable to our medium probe, so you should have the same footprint when you inspect over other materials. And yeah, do you have anything else to add?
Yeah, that's it. It works, but it's suboptimal. It's bulkier, it's a bit heavier because of the magnets and everything. But if that's all you have, in a pinch, it can work pretty well, except, of course, no dynamic mode.
Why is the encoder in dynamic mode not available with the GS probe?
Well, in general, for galvanized steel, we don't recommend you use dynamic mode, but it's even more important for this GS probe. The thing is, you have magnets, so you create a magnetic field into the jacket, and if you move the probe along during the acquisition, then the magnetic field inside the jacket is going to move, and that creates a very strong parasitic signal. It's very important, as I said during the demo, that the probe remains steady during the acquisition. So you shouldn't be moving, you shouldn't have a dynamic mode, you just concentrate on keeping the probe steady to get optimal data quality. One thing that we may add is for the transport of a probe.
Oh, yes.
Yes, so we sell this probe with this small metal plate, and basically if you put the probe on it, it's going to suppress the magnetic field. So it's just looping through the plate and not in the air, so now it's not magnetic anymore. This means that you can bring it with you in your luggage. It can travel by plane, so you can always bring it with you wherever you go.
It's also important for people who have medical implants to keep the magnet at least 30 centimeters away from yourself.
Yeah. As with every strong magnet.
Yes. Just a minute, we have some remaining questions. What minimum liftoff can be inspected with the GS probe?
Yeah, it's as you were saying a few minutes ago. We don't recommend you use it in contact, mostly because you can induce permanent magnetization into the component, which is going to affect the sizing. So we recommend half an inch liftoff.
At least 12 millimeters, yeah, at least. Well, there are still some questions remaining, but we wouldn't want to take too much of your time by going through all of them, so we'll answer individually by email. On behalf of Vincent and myself, thank you for your time today.
Yeah, thank you for being here. See you next time.